Welcome to this video. We're going to be taking notes on just a very small portion of the rest of 2.6, and then we'll also look at 2.7. This is for Math 126, 127. Okay, so what we're looking at today, we're going to finish up a little bit of information about graphing rational functions, and then we're going to look at polynomial and rational inequalities, where instead of an equal sign, we have less than, greater than symbols, so forth. Okay, so there's one additional form of a rational function that we want you to know about. It's called the graphing form. So to identify the graphing form, one of the things you're going to see is on the denominator, you would have a degree 1 binomial, and that would give you the location of a vertical asymptote at the root from that denominator. And then on this one, in this graphing form, we will have this constant k added onto the end. That is the location of the horizontal asymptote. You might wonder like where this comes from and what is it. Basically what this is this is if we did like long division from a rational expression. And what we would get is we would get this constant, and then this part right here would be the remainder. But it ends up giving us a very easy way to graph. And so, by the way, this form can only be used by a function that does not have a slant asymptote or any holes in the graph. If there's ever either one of those things, we wouldn't even try to put them into this form in the first place. You wouldn't be given anything in this form. To solve these, or to actually do the graphing, you would start with the horizontal and vertical asymptotes, and then again, you will still use an XY table to plot this, and then we would sketch the curve so that we are approaching the asymptotes on there. So these ones, we would not ever cross the asymptotes either. And again, since it's in this type of graphing form, I know that there cannot be a slant asymptote and there cannot be a hole in the graph. Like it's just literally not even possible in this form to have something like that. So the vertical asymptote would be right here on the denominator x, that 0 from the denominator x equals -2. I'll just draw that. If I don't throw things, I'll just draw that as a dotted line. The horizontal asymptote would be right here, that constant at the end. This is at y equals -1. Now that does not have a sign change. Okay, the vertical asymptote does, the horizontal does not. And so then to figure out a little bit more about where we would be able to kind of have this graph, let's go ahead and plot some points on either side. Maybe if I plot at a -3 and I substitute this in, I'd have 1 over -1 minus 1, which is -1 minus 1, which is -2. So I'll have the point -3, -2, so this will look something like this. And then on the next one over here, if I plug in perhaps a 1, I'll have 1 over 3 minus 1, which is -2/3. So, which is above this height of -1, so -2/3 would be somewhere around here. Now, it might be helpful to find out where that y-intercept is at. So if I substitute in a 0 here on this one, for the y-intercept, I would end up with 1/2 minus 1, which is -1/2, which is kind of right in here a little bit. I realized I just have an error here on where I plotted this 1 -2/3 +1. I'm not sure why I picked a +1. I probably should have picked a -1, but it's a point, so I mean I can add it in there. I'll actually do it now with a -1, and I end up with 1 over 1 minus 1, which is 0. In fact, there's my x-intercept, which is kind of nice. So my x-intercept is at -1, 0. The y-intercept we found as 0, -1/2. When I'm doing the domain and range here, domain would be all values of x, but not the x values for any vertical asymptote are holes, and there are no holes in the graph with this form. The range would be all y values except not the y values of any holes in the graph, which we don't have, or the horizontal asymptote. So those should both be on here. The end behavior would always approach the horizontal asymptote if there is one. So as x approaches positive or negative infinity, g, which is how we named this function, will approach -1. All right, let's take a look at this exploration. So if I'm looking at this function, which is graphed for us, by the way, if I wanted to see this in a different form, this is in factored form. The x-intercepts are at -2 and 3. Those are the zeros. If I wanted to see this, I could FOIL it out. That would allow me to see the y-intercept is -6. We can kind of see it right here. We could complete the square and do other things if we wanted to find the vertex, but this one's already graphed for us. This is asking us first, where is this below 0? Where is f less than or equal to 0? Well, what this means visually is this would mean below the x-axis, below and on, since it's or equal to, the x-axis. So this would be the closed interval from -2 to 3. And it would include those x-intercepts because of the or equal to sign. Totally different question now. Where is this function, for what intervals of x is this function below a -4? Well, -4 is like right here. That's the height of -4. So if I want to be below that, that's kind of looking at this region right here. So those x values would be from -1, it looks like, to 2. And I'm not going to include those places where I'm exactly at the height of -4 because of the open, it's just a greater than symbol, not or equal to. So what we're going to be doing is we're going to be solving these polynomial and rational inequalities. And what we want to do is we want to find out kind of where are some important values, some 0 values, and then find out where, because that might help us figure out kind of how to compare to one in inequality or not. So if it's a polynomial, you'll start off by getting a 0 on one side. That's going to be an example like number 2, we have a polynomial. And then I will want to solve that to see where are the values of x where there's a 0 or a discontinuity if it's a rational function. And then I want to kind of find the zeros of the numerator and denominator if they are both. And I'm going to set up a table to test some values. Now this will make more sense when we do it. And then I will then be able to find a solution that way. So there's an example here that I'll let you kind of look at on your own, but that example might make more sense after we've explored this a little bit. So starting with number 2 and number 3, these are both polynomial functions. We'll start off by getting a 0 on one side. And then I want to solve this inequality. Factoring is a good choice. If it doesn't factor, I would use the quadratic formula. So I'll factor this. The options for 15 are 1 and 15 and 3 and 5. And again, I want to end up with a 1. So I'm thinking if I use like a 3 here and a 5 here, I get this like 6x and 5x. Not sure I read it that way. Which can give me a 1 if the 5x is a negative and the 6x is a positive. I can just also kind of verify here that I would get that -15 when I expand this all the way out. Well, this gives me a couple x values that I'm going to use to explore. When x is 5 halves, we would have a 0. Now, I actually don't want to equal 0. I want to be greater than 0, but at 0, some interesting things are happening that we can use to explore. And also when x is -3. Now, x can't actually equal those values, just an FYI. The reason x cannot actually equal those values is because I'm not allowed to actually equal 0, and those would be the values that equal 0. But they're going to be points where we might have things change. What I'm going to do in my number line is I'm going to go ahead and include those points, -3 and 5 halves. I'll make sure and put them, the smaller one on the left. I'm not actually allowed to equal those points because I don't have an or equal to sign here. But these are going to be some places where maybe I have signs change from positive or negative. Remember the IVT, where we said that with the IVT for a continuous function, we could change like from a positive to a negative. We can only change from a positive to a negative by going through a 0. So these are where the zeros occur and where we might be changing signs. I'm trying to find out, where is this polynomial going to be bigger than 0? And so by looking at where it equals 0, I can start to examine where it might change from positive to negative or vice versa. What I'm going to do is I'm going to take this whole number line and split it up into intervals and like a little table. From the very left side of the number line up to the first 0, and then from that 0 to the next 0, and then from that 0 to infinity. And I'm going to kind of just make a little table where I'm going to explore what's happening on these intervals. Right at these interesting points of -3 and 5/2, my function equals 0, which I'm not allowed to equal 0. I must be bigger than it. But this is where I might change from a positive to a negative or vice versa. What I'm going to do is I'm going to take a value, an x value that's in each interval, and test it in my inequality. So something that's in between -infinity and -3, I could pick any number in there. I'll just pick something easy. I'll pick -4. And I'm going to go and I'm going to plug that in. I usually plug it into the factored form. I find it easier to simplify this. And all I really care about is when I plug those numbers in, do I get positives or negatives? I'm comparing to 0. And so if I plug a -4 into the first factor, 2 times -4 minus 5, that's a negative. I don't actually care about the value of the number, just its sign. And then the next factor, -4 plus 3, well, that's also a negative. Well, negative times a negative is a positive, and it is greater than 0, which is what we're looking for. So what this means is that all of the values in this region are going to be part of my solution, because I'm looking for places where I'm larger than 0. If I look at this next point, I'm going to test an x value within this. Maybe I'll pick 0. And so again, I'm going to use my factors. If I plug in a 0 to the first factor, I'd have a negative. If I plug it into the second factor, I have a positive. I end up with a negative, which is not smaller than 0. And or is not bigger than 0. It's smaller than 0. That's not what I want. I want things larger than 0. So I'm not going to select this region in between -3 and 5/2. This is where I would have negative values. And if I pick 5/2 and infinity, and I just test a value in there, maybe I'll test x equals 3 is bigger than 5/2. I could pick 10 or 100, whatever. If I plug in a 3, I'd get a positive for the first factor and a positive for the second factor. A positive times a positive is bigger than 0, so I want that to be selected. Now, when we do these, we have two different parts of our solution. We have the graph, which I've got right here, and then I need to write an inequality to model this graph. So I can look, and I'll just use interval notation. From -infinity to -3, notice how I've used an open circle, and then the union of that with 5/2 and infinity. This is going to be my solution. Now, there's one other thing to think about this. If I graphed this quadratic, which would be kind of a pain, but like if let's say I set this on a coordinate system and I graph this, I would have zeros at -3 and 5/2. This is opening upwards. This looks something like this. This is what the quadratic looks like. What we're looking for is, where are we above 0? Where are we greater than 0? Notice all of those heights are bigger than 0. And same thing over here. We wouldn't want anything in between the -3 and the 5/2 because we are actually smaller than 0 there. So sometimes if it's a function that maybe you're really familiar with how the graph looks, you might be able to avoid the kind of chart and testing points. However, the chart and testing points is a skill that ends up becoming important in later topics, so it's not a bad thing to do it that way. Now, with something that's like a degree 3, that may or may not be as easy to do with the graphing method, but I'll still show you how to do that. I'm going to start off by getting a 0 on one side, so I'll just kind of reorganize this information. And I'm going to solve this by factoring. This one I will use factoring by grouping, so I'll take out an x squared from the first terms and a -4 from the next terms. And I'll take out the GCF of x plus 1 leaving me with x squared minus 4, which can be factored as x plus 2 and x minus 2. So my zeros are at -1, +2, and -2. Those are where my zeros are at. So on my number line, -2, -1, I'm just putting them in order, and +2. Now the question is, should I use an open circle or a closed circle for these? Well, we are allowed to equal 0. So I'm going to go ahead and use closed circles. I'm actually allowed to equal 0. So where these x-intercepts are, where these zeros are going to be values that I'll accept. I'm going to make a table, and I'm going to separate my number line starting at -infinity and going to each x-intercept, or each solution, or each zero, however you want to say that, and all of the regions in between them all the way through +infinity. And I'm going to just test some values inside each interval. So for the first one, I'll test anything in between. You could pick any x value in between -infinity and -2. I'll pick -3. And I'm going to use the factored form to test it. If I plug a -3 in, the first parenthesis would be a negative. So would the next one. So would the last one. I'd end up with a negative, which is less than or equal to 0. So this is part of my solution. If I then test something in between -2 and -1, I'll pick like -1.5. And I plug that into my yellow factored form here, I'd end up with a negative times another negative times a positive. I'd end up with a positive, which is actually greater than or equal to 0, which is not the sign I'm looking for. I'm looking for where we have negatives or at the height of 0. So I will not shade in this region. I am not including that as part of my answer. My next region, I will test something in between -1 and 2, such as 0. If I plug in a 0, I get a positive for the first factor times a negative times a positive, which is a negative, which is less than or equal to 0, which is what I'm looking for. So I do want this region. And then if I test something to the right of 2, maybe I test something like 100. It doesn't actually matter as long as it's in the interval between 2 and infinity. You can pick any x value in that interval. I'd end up with a positive for every factor, and when I multiply that together, I get a positive. I want it to be less than or equal to 0. I'm not, so I will not pick that region. So how would I write this? I would write my answer. So the graph is part of my answer, as well as this interval from -infinity to -2. Also from, oh, hang on, this is going to include the -2, so I will use a closed bracket. I will also include from -1 to +2, including those endpoints. So this is the solution set along with the graph. Could we use the graphing method for doing this? Absolutely, you can, if you know how to graph this. So like, let's say, I don't know, here's my little coordinate system. I'm going to use what we know about end behavior here. So for this polynomial, since the leading coefficient is positive, on the right-hand side, I'm going up. On my left-hand side, since this is an odd degree, I'm going down. And I don't have any multiplicity for these zeros, which means that yet each of these zeros, I'm crossing the x-axis. I'm not bouncing. So this, I don't know the actual heights of these. Okay, I'm just getting a shape. Something like that. And notice what I wanted is, where are all the x values where we're below the x-axis? And those are the x values that I chose. That's what was shaded on my number line. So if you know enough about the graph to be able to draw a sketch by using the zeros and end behavior, then you can kind of avoid the table. And that's a totally appropriate method as long as you feel like you understand it. All right, let's take a look at these rational functions. With these rational functions, okay, so this one we have a rational inequality this time. So we have a fraction. We still want to get a 0 on one side. We're going to have a little bit more algebra to do when we have to do this, but we can handle it. So I'm going to rewrite this as x plus 1 over x plus 3 minus the number 2 is greater than or equal to 0. Well, one of the things that we know about rational expressions is that we can only combine them if they have a common denominator. So what I'm going to do is I need this minus 2 to have a denominator of x plus 3. So I can multiply it by the form of 1, x plus 3 over itself to try to make that happen. What would end up then is I'd have the common denominator x plus 3. On the numerator, I'd have the x plus 1, and then I'd have minus 2x minus 6. Be careful with that minus 6. Sometimes people put plus 6. They don't attach that negative as they distribute here. So I'd end up with negative x minus 5 over x plus 3 is greater than or equal to 0. I'd recommend that you make sure everything is factored at this point. So I'm actually going to factor out a negative on that numerator to kind of help me here. This is going to allow me to identify the values of x that are important. There's actually 2 of them that are important. We need to consider the values of x from both the numerator, x equals negative 5. We are allowed to equal exactly negative 5 because we are allowed to equal 0 because of this or equal to bar. And the denominator, x equals negative 3 is the root. However, we are not ever allowed to have a 0 on a denominator. This is a domain restriction. So any 0 that comes from a denominator, you will write it as x is not allowed to equal that number, which is important because then when we do our number line, the numbers that are important here would be negative 5 and negative 3. This is where we might be changing signs from that 0. We want a closed circle on the negative 5, but on the negative 3, we need an open circle. So it'll look something like this. I'm now going to go ahead and test these values here. So I'm going to break up the number line from negative infinity to negative 5, from negative 5 to negative 3, and then from negative 3 to positive infinity. I'm not worried about open and closed circles at this point. I'm just going to be looking at things in between. So I'll test an x value in each region. Maybe I'll test x equals negative 10. I like to use the factored form. That's what I do. And again, I'm comparing this to the 0, and I'll use that inequality. So I have a negative factored out with another negative inside. On the denominator, I'd have a negative. So I'd end up with a negative, which if I compare that to 0, is not true. So this one is a no. So I will not end up here with the sign that I was hoping for, which is greater than or equal to 0. So I will not shade to the left of the negative 5. If I test something in between negative 5 and negative 3, maybe I'll do negative 4. I'd have a negative times a positive over a negative. So I end up with a positive, which is indeed greater than or equal to 0. So I do want to shade in this region. Notice how one of those has an open circle, one has a closed. And then if I test something bigger than in negative 3, maybe I test 0. I'd end up with a negative. And if I plug in a 0 here, I'd have a positive inside that parenthesis and a positive underneath. So I get a negative, which is not greater than or equal to 0. I don't know why I wrote it that way. So I will not shade in that region. This is my graph, which is part of my answer. My inequality is I will go from negative 5 to negative 3. Notice the bracket at the negative 5 and an open circle parenthesis at the negative 3. This one is still possible to solve with the graphing. It's just not necessarily easy to do so, but we could do horizontal and vertical asymptotes and use the graphing method to see where we're above and below the x-axis from this highlighted one. But honestly, I think the amount of time you would spend doing it that way is less than the amount of time you spend on the table, so I'm not going to really model that one. Number 5. This one's already factored for us. We also already have the 0 on one side, which we need to get that 0 always. So x-intercepts will occur when x is 2 and x is 7/2. However, based on this inequality symbol, I'm not actually allowed to have an actual 0, so I'm going to put not equal to here. There's still the interesting points. I still want to really consider, this is where we're going to change from positive to negatives, but I'm going to use open circles for both of them because of that less than that's happening. Now, something that I want to mention, for every problem that we've done so far, you might have noticed that every region kind of toggles back and forth between being selected and not selected. You might make a false assumption that that's always true. This is going to be an example where that is not true, and we'll talk about why. But I'll break up the number line from negative infinity to 2, from 2 to 7/2, and from 7/2 to positive infinity. And we'll test this. So if I test something in between negative infinity and 2, maybe I'll test 0. You could certainly pick a different number. When I plug that in, I get a positive, that is then squared, which remains a positive, times a negative. I get a negative, which is less than 0, and that is what I want. So I will be graphing and selecting this region. All right, if I take a look at this next region, something in between these values might be something like x equals 3. If I plug in a 3, I get a positive, which when I square it is still positive, times, let's see, 3 minus 7/2. 7/2 is 3.5, so this will be a negative. And interestingly enough, I still got a negative, which I want. So I'm actually, surprisingly, going to not toggle back and forth on this one, and I'm going to be staying right here at this negative, which is surprising. Okay, and then if I pick something larger than 7/2, maybe I'll pick x equals 10, whatever. I'd get a positive that is squared that stays positive times another positive. Positives are bigger than 0, so I do not want that region. So this is my graph. And then my interval that I want would be from negative infinity to negative 2, union with the next interval from negative 2 to 7/2. This is how you write it to show that you've skipped over that negative 2. Does the graphing method work on this? Yes, you just have to be careful and make sure you really do understand about how the end behavior works. I'll just kind of plot where I think a 0 is. Okay, if I expanded this out in here, I'd have this negative x, which will get squared, which will become a positive x squared times another x, and my leading term is x cubed, plus a whole bunch of stuff. Since I have an x cubed on the right-hand side, I would be going up. On the left-hand side, I should be going down. But here's what's interesting on this one. On this one, what ends up happening is this factor where x is 2, because it's squared, we don't cross the x-axis here. What we do is we bounce off of the x-axis. We must at some point curve back up. It must look something like this. So since I wanted to see everywhere I am less than 0 or below the x-axis, we're below that x-axis everywhere except for right there at the 2 where we bounce off and touch the x-axis. So that's how the graphing method could work here. I think most people on this one would still probably use the table. These next ones are just some additional practice with graphing rational functions because it is a topic that students sometimes struggle with. So you may or may not feel like you need this, but I'll go through and do these examples in case it would be helpful for you. If you're feeling pretty confident, you might just want to pause the video and then try them if you're like kind of confident, and then restart it to see if you did them properly. All right, so I'll factor out a GCF and the difference of two perfect squares on this one. We have a hole in the graph when x is 5, that is the x coordinate. Now the equivalent expression for this is x over x plus 5. So if I want to find out the y coordinate of that, which I'll need, I'll plug in a 5 into my simplified expression, and I get 5 over 10, which reduces to 1/2. So I have an open circle at 5, 1/2. I have a vertical asymptote at the other 0 on the denominator, which is x equals -5. And I have a horizontal asymptote at y equals 1, and that's because I have the same degree on the top and bottom. So I'm just going to compare a ratio of those leading coefficients 1 over 1. The y-intercept can be found by substituting in a 0 to any of the equivalent expressions. I like to use the simplified one. I get 0 over 5, which is 0. The x-intercept, since the y-intercept is 0, the x-intercept is also 0. You can see it actually right here. The factor on the numerator that was not repeated as the whole is an x-intercept. So, I mean, I feel like I have enough points on this right-hand side to graph this. Something like this. On the left-hand side, I'm not really sure if it's above or below the horizontal asymptote, so I'm going to test a point at -6. I like to use the reduced one. I get -6 over -1, which is +6. So this should look something like this. Remember, I'm just sketching. Okay, so my domain. My domain will be all values of x except for the x values from the whole and the vertical asymptote. I'll put them in order from least to greatest. The range will be all y values except the y values from the whole in the graph, 1/2, and the horizontal asymptote. Just ordering those. The slant asymptote, there will not be one because there's a horizontal asymptote. And the end behavior, both the left and the right sides will approach the height of the horizontal asymptote, which was a height of 1. For the next extra practice, I'll see if this one factors on the numerator. So let's see, I'll factor this as 2x and x. My factors of 7, the only ones are 7 and 1. So 7 and 1. I think we actually explored this one for the asymptotes before, but now we'll use it for graphing. I want a -5 when I combine them. You can kind of explore and see, oh, actually that does not work. I take that back. This will not actually factor because if I tried to expand it, you might see that that's a -7. If I switch around my 7 and 1, it doesn't factor. So this one does not factor out. Okay, so I do have a vertical asymptote. The vertical asymptote is at x equals 2. I'll draw that as a dotted line. The horizontal asymptote, there isn't one. The degree is larger on the numerator than the denominator. And since they are 1 degree apart, there is a slant asymptote. I'll use synthetic division to find it. Remember, you are multiplying and adding. We actually do not care at all about what the remainder is, but the slant asymptote would be at the line y equals 2x minus 1. I'm just going to graph this with a y-intercept at -1 and a slope of up to and over 1. I will connect this with a dotted line. Now, this doesn't mean there are no x-intercepts. There probably is, but it just means it didn't factor. So if I wanted to find them, they didn't actually ask me to. If I wanted to find them, I'd have to use the quadratic formula since my numerator won't factor. I'm now going to test a couple points on either side of my vertical asymptote so I can try to see where they would be at and plot this a little bit. Maybe I'll test x equals 1. So if I plug in a 1 on the numerator, looks like I get a 4, and on the denominator a -1. So we have the point 1, -4. I'm thinking this is looking something like this. It just says sketch. It's not a super precise graph. Do I really know exactly how tall that mountaintop is? Not really. I'm guessing. But I know it's kind of in that region. It's bounded by those asymptotes. And then I'll test something on the other side of my vertical asymptote, such as 3. A little harder to evaluate this. This would be 2 times 9 minus 15 plus 7. What is that? On the top, I guess 18 and 7, 25 minus 15 is 10. And on the bottom, I'd have a 1. So this is the ordered pair 3, 10, way, way, way up here. So I'm thinking this fits somewhere in here. Do I know how far deep down this like kind of little valley goes? I really don't. I'm not worried about it because it's just a little sketch. But I have the items in the right placement. All right, let's take a look at this one. I want to find the equations of all asymptotes and the coordinates of all intercepts. This numerator might be better understood if it's reorganized. So I am going to factor this. The numerator factors as x plus 2 times x minus 2. The denominator does not factor with real numbers, and when I'm graphing, I'm only interested in real numbers. There are no holes. There is no vertical asymptote because there are no zeros on that denominator. If you're not convinced about that, the fact that it doesn't factor is one way to know that. But if you tried to solve this perhaps by square rooting, you might notice I get imaginary numbers. So there are no zeros on that denominator, thus there is no vertical asymptote. The horizontal asymptote does exist. If I compare the degree, I have a 2x squared degree 2 on the top and bottom. The ratio of the leading coefficients is 1/3. And if there's a horizontal asymptote, there is no slant asymptote. So there's only one asymptote here, which is interesting. We're not actually graphing this one, but we'll check it out on the graphing calculator so you can see it. We also want the intercepts. Well, the x-intercepts are going to be any factors of the numerator that are not repeated on the denominator. So my x-intercepts, there's 2 of them, will be at -2, 0, and +2, 0. To find my y-intercept, I'm going to substitute in a 0. On the top, I'd get a -4. On the bottom, I'd get a 1. So my y-intercept is at 0, -4. Let's just check this one out on the graph and make sure that the things that we think we're seeing are what actually shows up on the graph. Okay, so on the top, we had x squared minus 4 once I reorganized it. And the denominator was, I think, 3x squared plus 1. Notice how I'm grouping these in parentheses. And let's graph it and see what we can see. Interesting. You might notice that there is indeed a horizontal asymptote here, and it's small. It's at a height of 1/3. In fact, maybe I'll just mess around with the heights here really quickly so we can get a better sense of what's happening. Oh, those are the x's. Well, that's okay. Maybe I'll make these -5 and 5. Let's change the heights. I'll go from -3 to 3 so we can just see it a little bit better. We'll count by ones. Oh, my y-intercept was at -4, so let me make sure we can see that. So you might be able to tell that this looks like about 1/3, that height. We have x-intercepts at -2 and +2. There's the y-intercept at -4. This is a super interesting graph. Really a kind of surprising one, but that's how it ended up looking out. And I didn't have you graph it because it is one that's a little harder. You'd probably have to plot a fair amount of points in order to graph this one. Super weird when we don't have a vertical asymptote. All right, this is the end of the notes for this video.